The second part of my playlist is devoted to the vector derivative. We want to be able to differentiate multivector valued functions defined on, and perhaps only on, manifolds. The vector derivative does this. It generalizes the gradient on Rn. Before discussing the vector derivative, I want to say a bit about the gradient operator. It's an aside from a straight line to the fundamental theorem, but it's an important aspect of geometric calculus, and so I need to discuss it. So, let's define the gradient. We'll start with an orthonormal basis, E1, E2 for R2, and a multivector valued function, f, defined on some open subset of R2. Here's the definition. This is familiar, except that usually the partial derivative is written to the left of the basis vector. For a scalar valued function f, this doesn't matter because scalars commute with vectors. But for a multivector valued function, this partial derivative need not commute with E1. So we have to make a choice, and I choose in this playlist to place the partial derivatives on the right. Now, I've defined the gradient only for R2, but it's perfectly obvious how to extend to Rn. I'll often use R2 as a stand-in for Rn when it makes the notation simpler to read, and it's obvious how to generalize to higher dimensions. Next, I introduce a vector operator, del, which is equal to this. The coefficients behave as scalars. They commute. This is the equality of mixed partial derivatives, and they preserve grades. This partial derivative has the same grade as f itself. Then you can think of the gradient of f as a geometric product, the vector del times the multivector f, written this way, and that expands to this. We're now ready to introduce the divergence and curl. We'll start out with the gradient from the last slide. The vector del, geometric product f, which expands to this. The divergence is the vector del inner product f, which can be written this way and expanded. And the curl. Recall that in geometric algebra, we replace the cross product with the outer product, the curl then being the vector del outer product f, which looks like this, and which expands to this. Recall the fundamental identity of geometric algebra. The geometric product of two vectors is equal to their inner product plus their outer product. This can be generalized, replacing v with a general multivector m. Simple counterexample so that I can't then also replace u with a general multivector. Well, in the same way as this equation holds, this equation holds. Vector times multivector equals vector inner multivector plus vector outer multivector. The gradient is equal to the divergence plus the curl, unifying the divergence and the curl into a single operator. The gradient operator has the wonderful property that it's invertible. If I have a multi-vector valued function on an open set U in R2, I can express the invertibility of f by saying that f is determined by its gradient on U and its function values on the boundary of U. Next, we need the notion of the dual of a multivector. I'll start with the definition, that of a unit pseudoscalar. I've illustrated with the unit pseudoscalar of G3. It's obtained by multiplying members of an orthonormal basis for R3, giving the unit pseudoscalar I. If I choose a different orthonormal basis with the same orientation, I'll get the same unit pseudoscalar. And now we can define the dual. The dual of a multivector, denoted M star, is obtained by multiplying the multivector M by I inverse on the right. This I inverse is easy to come by, as I now show. Here's the unit pseudoscalar for R3, and here is the members of the unit pseudoscalar, but given in reverse. Let's multiply them. E3 times E3 is 1, so that goes away. E2 times E2 is 1, so that goes away. And finally, E1 times E1 is 1. That's all we're left with. So that tells us that this is the inverse of this, which is I. Okay, we're ready for the geometric interpretation of this dual. And here it is. I have a blade B, which represents a certain subspace S. We know that blades represent subspaces. Then B star, the dual of B, represents the orthogonal complement of S. Vector algebra provides no simple algebraic way to pass from a subspace to its orthogonal complement. Vector algebra doesn't even represent subspaces. Let's look at the most important case of this orthogonal complement. In R3, here's the origin in R3, and here's a vector. That vector represents a certain subspace. Here's a bivector. That bivector is a subset of a two-dimensional subspace. And I want the vector in the bivector to be orthogonal, as indicated here. And I want the length of V to be equal to the area of B. Then V and B are each other's duals. The dual of V is B, and the dual of B is V. Well, not quite. If I take the dual of V to get B, and then I take the dual of B, I don't get V. In fact, I get minus V. But that's okay, because minus V represents the same subspace as does V. A couple of identities. The dual of an outer product is an inner product, but I have to replace the rightmost member of the product with its dual. And exactly dually, the dual of an inner product is an outer product, but again, I have to replace the right member by its dual. And finally, the dual of the outer product of two vectors in R3 is equal to their cross product. So I still have the cross product if I need it. This slide and the next compare the formulations of Maxwell's electrodynamic theory in vector calculus and in geometric calculus. In vector calculus, the magnetic field is represented by a vector. Usually, the vector is denoted in uppercase B, but I have another use for uppercase B, which is this. In geometric calculus, the magnetic field is represented by minus the dual of this vector, which is a bivector. Of course, it's given by this. In vector calculus, the magnetic field is represented by a vector. In geometric calculus, by a bivector. The bivector representation has many advantages. Here's an example. I've indicated here a loop of wire carrying a current. Such a current will generate a magnetic field. The magnetic vector representation of the field in vector calculation is this vector. The vector is orthogonal to the loop. Its direction is given by the right-hand rule. Wrap the fingers of your right hand around the loop in the direction of the current, and your thumb will point in the direction of B, little b. The representation of the magnetic field in geometric calculus is a bivector, and I've indicated the bivector here. The area of this rectangle is equal to the length of this vector. The orientation of the bivector is given directly, geometrically. No human intervention required. The orientation is the same as the orientation of the current. Now let's reflect the whole setup in a mirror indicated here. So the current loop reflects to this current loop. The bivector reflects to this bivector, and you'll notice that the orientation of this bivector is correct. It's the orientation of the current. The reflection of B I've indicated here, but it's not the representation of the magnetic field, as you can check applying the right-hand rule. Rather, the proper representation is the negative of this reflected B. For this reason, the magnetic field is, at least in this sense, not a vector. People instead call it a pseudovector. Maxwell's equations are the equations which govern the electromagnetic field. Maxwell's theory is usually formulated using vector calculus, R3 vector calculus. I want to compare that formulation with the geometric calculus formulation in G3. So let's start with the vector calculus version. Maxwell's equations in vector calculus represent the electromagnetic field with two separate vector fields, the electric field E and the magnetic field B. Maxwell's equations in empty space, where there's no matter, are given by these four equations, four differential equations involving E and B. I'm going to play with these equations a bit and put them in a different form. So first, these are the same. The dual of the outer product, as I mentioned, is the cross product, so that explains this. Here, I've simply taken the dual of both sides of the equation. And the same here, remembering that the dual of an inner product is an outer product, and I have to replace the right member with its dual. So these four equations are equivalent to the original four. Recall the magnetic bivector field, which is given by this formula, where B is a bivector orthogonal to B, and I want to now substitute big B for little b. And I get these equations. Again, these are the same. The dual of an outer product is an inner product. I have to replace B with its dual. Well, its dual is minus big B, but I've compensated for that by the change in sign here. The dual B star is minus B, and we'll take care of the minus sign. The dual of a cross product is a minus an outer product. So we get this. The dual of B, little b, is minus big B, but since I have a 0 on the right, I can have it just as I've shown. So, the original four equations in geometric calculus notation are given by these four equations. But I'm not done yet. In geometric calculus, the electromagnetic field is represented by a single field, vector field plus bivector field. I can't do this in vector calculus. I can't add the electric vector field and the magnetic vector field. If I add them, they become mixed up and they lose their separate identities. Then I claim that the four Maxwell equations that you see are equivalent to this single Maxwell equation. And the proof is straightforward. This multivector has a scalar part, has a vector part, it has a bivector part, and it has a trivector part, all of which are equal to 0. And setting those four equal to 0 gives me exactly the four Maxwell's equations above. So we can get rid of those four, and we have this pair of equations. This represents a magnetic field, and this is the differential equation satisfied by that electromagnetic field. This electromagnetic field obeys the wave equation. It's an electromagnetic wave, and it's easy to see that it obeys the wave equation. I write down the left side of the wave equation. Looks like this, and I want to get 0. Well, if I factor this, I get this, and this, by Maxwell equation just above, is equal to 0. And there we have it. This is a much more difficult thing to do in vector calculus, showing that the vector calculus electromagnetic fields, E and B, each satisfy the wave equation. And just to finish up, I'll add the geometric calculation formulation of the Lorentz force. So we have here electromagnetism in G3. We can now return from our detour in discussing the gradient to take up the vector derivative. We need a couple of concepts. The first of which is of a reciprocal basis. I start with a basis for Rn, then it is a theorem that there is a unique reciprocal basis, B super I being a superscript and not a exponent, satisfying these two equations. You see right away that an orthonormal basis is its own reciprocal basis. Here's an example. I'll start with a black basis here, B1, B2. Then the blue basis is the reciprocal basis. For example, if I take the inner product of B super 1 with B sub 1, I'm supposed to get 1. And if I take the inner product here with the inner product here, I do in fact get 1. If I take the inner product of B super 2, this vector, with B sub 1, I'm supposed to get 0. If I take the inner product, I indeed do get 0. Recall our earlier discussion of the tangent space T sub p to a manifold at a point P on the manifold. We need a basis for that tangent space. So I'll parameterize a surface, x of uv, x of uv. uv is a point Q, and x of Q is P. I'm going to abbreviate this partial derivative to this. By definition, that partial derivative is this. And earlier, we had another notation for this, which was given by this, where this is a tangent vector to the surface at P. Well, never mind all that. The important point is that since this is a tangent vector, this is a tangent vector. And the theorem is that this pair is a basis for the tangent space. Recall that we wanted to differentiate multivector valued functions on manifolds, and that the vector derivative does this. It generalizes the gradient. I'm now finally ready to define the vector derivative. I'll start with the parameterization of a surface. We just learned that this is a basis for the tangent space. I'll denote this by the reciprocal basis. Here is a multivector valued function defined on the surface, and here is its vector derivative. You see, it's rather like a gradient, except I use reciprocal vectors here rather than the vectors themselves, the reason being that x sub u and x sub v aren't necessarily orthogonal, so I need to use, in fact, the reciprocal vectors here.